Hello friends, let us now learn some important points about the applications to diagnostic radiology. The applications of attenuation to diagnostic radiology. So, first, photons in an X-ray beam enter a patient with a uniform distribution, and the energy pattern in a specific pattern of distribution. Transmitted rays carries the X-ray image, whereas their photons also carry a memory of attenuated photons. The transmitted and attenuated photons are equally important. If the photons are transmitted completely without attenuation, this results in black film. If all photons are transmitted, the film will be uniformly black. If all the photons were attenuated, the film will be uniformly white. So in neither case there would be an exchange of there would be an X-ray image. So image formation mainly depends on differential attenuation between the tissues. Some tissues attenuate more X-rays than the other, and the size of this differential attenuation determines the amount of contrast in the X-ray image. To determine the differential attenuation, we consider a radiograph of hand. So we only have to discuss two types of tissues, bone and soft tissue. So I would like to draw a figure. A soft tissue is approximately equal to water. Water is used to represent the soft tissue. So this is a graph showing the linear attenuation coefficient on y-axis and the kilovoltage or energy in the x-axis. So this is the energy, and so now we see the differential attenuation coefficients of compact bone and water. Water is used to represent the soft tissues. Higher the linear attenuation coefficient, higher is the attenuation. So greater the linear attenuation coefficient, greater is the attenuation. So X-ray attenuation is greatest in bone when compared to water. So bones show up as holes in the transmitted pattern. We see these holes in the white layer of the film. So if you see so these are the different attenuations like coherent scattering, then we'll see the photoelectric effect, coherent scattering, Campton scattering, and finally photoelectric effect. So this is Campton scattering, and these blue dashed lines are for photoelectric effect. Okay, so if you see the linear attenuation of the water, linear attenuation coefficient of water at 20 kilo electron volts is 0.77 millimeter per millimeter, whereas the linear attenuation of bone at 20 kilo electron volts is 4.8 per centimeter of water. So this is 0.77 and this is 4.8. So the picture is not that good, but so if you see, this picture is not that good, but just a minute. Yes, this picture is not that good because the this is 0.7, this is 4.8. The difference visually is very less, but in reality the water has linear attenuation coefficient of 0.77 per centimeter, whereas bone has linear attenuation coefficient of 4.8 per centimeter. So bone has linear attenuation coefficient a lot more when compared to the water. With such a large differential, X-ray image will display a great deal of contrast. At an X-ray beam of 100 kilo electron volt, the differential attenuation is not that large, but bones still attenuate more X-rays than water. But now the difference is only in the factor of 0.6. This picture will attenuate will illustrate one more point. Linear attenuation coefficient is actually made up of three separate coefficients of coherent coefficient of three basic interactions. So one for each basic interactions. So we have linear attenuation coefficient for coherent scattering, for Campton scattering, and for photoelectric effect. So each contributes its own component to the linear attenuation coefficient. At lower photon energies of 20 kilo electron volts, most of the difference in X-ray attenuation between the bone bone and the soft tissue results from the difference in the photoelectric reactions. Bone contains calcium, which is relatively higher atomic number than the soft tissue. So the photoelectric effect will predominate in bone when compared to soft tissue. Whereas at higher photon energies, the difference in the X-ray attenuation between the bone and the soft tissues is almost entirely has a result of difference in number of Compton reactions than the photoelectric reactions, because few photoelectric reactions occur in either bone or soft tissue at 100 kilo electron volt. When Compton reactions predominate, the differential attenuation entirely depends on the density. The reason is that denser materials have more electrons available to undergo reactions. So the same thing is expressed here. So bone at lower energy there is maximum photoelectric effect, whereas at higher energy there is Compton reaction. So you can see I have changed the picture, making this compact bone a little even more bigger when compared to the soft tissue. Okay. So if you summarize photoelectric effect at lower energy, there are two possibilities, one low atomic number and high atomic number. High at lower energies, in higher atomic number photoelectric effect predominates. So mu of photoelectric effect is more for compact bone when compared to water, whereas at higher energies, both for high and lower atomic number, the photoelectric effect decreases and Compton reaction will predominate. So mu per Compton reaction will predominate, and this Compton reaction depends on the density of the material. On increasing the denser, that is denser materials have more electrons available to undergo Compton reaction. The next important thing is the next graph, which is for Compton linear attenuation coefficients. So on x-axis, Compton linear attenuation coefficient versus the energy for water, compact bone and sodium iodide. So from water to compact bone, the number of Compton reactions decreases only slightly with increasing energies. So the energy beam, as the energy beam increases from 20 to 100, the Compton linear attenuation coefficient for water will decrease, whereas the Compton linear attenuation coefficient for bone decreases about 20%. So this shaded region is mass attenuation coefficient, that is Compton mass attenuation coefficient. So this shaded portion is Compton mass attenuation coefficient. Then this is the photoelectric effect. Mass attenuation, this purple color is the photoelectric effect mass attenuation coefficient. So if you see, the number of Compton reactions decreases only slightly with decreasing in X-ray energy, with increasing X-ray energy. The number of Compton reactions decreases only slightly with increasing X-ray energies, as the energy of X-ray beam is increased from 20 to 100 kilo electron volt. Compton linear attenuation coefficient for bone decreases by 20%, while photoelectric attenuation decreases more than 99%. This shaded portion is the Compton mass attenuation coefficient. The mass attenuation coefficient indicates the amount of attenuation per gram, and it is not dependent on density. So as you see, 1 gram of water attenuates more X-rays than 1 gram of bone by Compton or sodium iodide by Compton reactions, because water has more electrons per gram, whereas sodium iodide has fewer electrons per gram than bone because of high iodine number. So a gram of sodium iodide attenuates fewer photons by Compton reaction than either a gram of water or bone. Nevertheless, even the Compton scattering is only a type of basic interaction. There is a still difference in the X-ray attenuation between water, bone and sodium iodide, and this will favor This in favor of higher atomic number absorbed, but the difference is entirely on the density. So important thing is mass attenuation coefficient. Mass attenuation coefficient is directly proportional to the number of electrons per gram. Water has more electrons per gram, so more maximum mass attenuation coefficient, whereas iodine having less electrons per gram has less mass attenuation coefficient. So water, 1 gram of water absorbs more electrons per gram than 1 gram of iodine. Fat. Fat and water are always difficult to differentiate radiographically. The effective atomic number of fat is 5.9 and effective atomic number of water is 7.4. So, they can be differentially attenuated by photoelectric attenuation using low energy techniques, because photoelectric attenuation is directly proportional to the atomic number cube. With higher energy radiation, so if you see with So the only way to differentiate is by low energy techniques. But if you use higher energy radiation, Compton effect will predominate. Differentiation if it is used for low energy techniques. If higher energy techniques are used, then Compton reaction will predominate, because of the differentiation between fat and water depends on density and number of electrons per gram. So it is very difficult to differentiate fat and water using Compton reactions in high energy states. Water has a higher density, so it has fewer electrons per gram, whereas whereas fat also has lesser electrons per gram. So the net result, the number of electrons per gram for both water and fat is same. Water has approximately 2% more electrons per gram than fat, which is very small difference to demonstrate only Compton reaction. So as a result, a significant difference in attenuation between fat and water is only possible by using photoelectric effect using low energy techniques. Thank you.